Hey there, have you ever wondered how we know so much about the invisible world of molecules? I mean, we can't see them? Well, it turns out one of the best ways is to just shine a light on them. Today, we're going to uncover this incredible story that's hidden inside a molecule's spectrum, a story of energy, quantum leaps, and yeah, even the exact moment a bond is going to break.
So that's really the big question we're tackling. How on earth can something as simple as absorbed light reveal the precise breaking point of a molecule? I know it sounds a little like science fiction, right? But stick with me, and by the end of this, you'll see exactly how it's done. Here's our game plan. First, we'll look at that initial moment when light and a molecule meet. Then we're going to zoom right in on the electron's quantum jump. After that, we'll get into the rule that controls this jump, see what happens when things go sideways and the molecule actually breaks apart, and finally, we'll learn how to read all the clues left behind in this spectrum. All right, let's jump right in. Part 1. What is actually happening at that initial moment of contact when a single photon of light smacks into a molecule?
So this whole field is called electronic spectroscopy. And at its heart, it's all about what happens when a molecule absorbs a photon of UV or visible light. But here's the thing, it can't be just any photon. It has to have the exact right amount of energy. If it's a perfect match, the molecule soaks up that energy and uses it to kick one of its electrons up to a higher energy level.
Now, it's not the entire molecule that gets in on the action. Nope. Only specific parts, which we call chromophores, are the ones responsible for absorbing light. A classic example? The double bond in a simple molecule like ethene. That's the hotspot. That's where everything happens. Okay, so we know an electron gets this jolt of energy, but where is it coming from and where is it going? Let's take a closer look at what's at the heart of this wild quantum leap. You know, in the world of quantum chemistry, we have these fancy terms. The electron starts its journey in what's called the HOMO. That stands for highest occupied molecular orbital. Just think of it as the highest energy level that actually has an electron in it. When it absorbs that photon, boom, it jumps to the LUMO, the lowest unoccupied molecular orbital. It's the very next rung on the energy ladder that's empty and waiting for it.
And these jumps, they kind of come in different flavors, and each one leaves a very different fingerprint on the data. You've got your pi-to-pi star transitions, which you see in molecules with double bonds, and they give these really strong, intense signals. Then you have n-to-pi star transitions, which involve electrons that aren't in bonds, lone pairs, and these are usually much weaker. Just by seeing which kind of jump happened, chemists can start to figure out what they're looking at. So let's just visualize this for a second. Before any light shows up, you've got this picture. The electron is just chilling in its ground state, its happiest, most stable, lowest energy position, right there in the HOMO. Everything is calm and stable.
Then, bam, a photon with the perfect amount of energy arrives. It gets absorbed, and all its energy is dumped directly into that electron, which instantly, and I mean instantly, leaps up to the LUMO. It's now in what we call an excited state. And again, the key is that the photon's energy has to be a perfect match for that energy gap. But here's the cool part. This leap isn't just random chaos. It follows a very strict rule that explains why the lines we see in a spectrum have the shape and intensity they do. And believe it or not, it all comes down to pure, unadulterated speed. How fast are we talking? About 10 to the minus 15 seconds. That's a femtosecond. To give you some perspective, a femtosecond is to 1 second what 1 second is to about 32 million years. It is just mind-bogglingly fast. Think about it this way. The electron's jump happens so ridiculously fast that the big, heavy atoms in the molecule have absolutely no time to move or even vibrate. For that tiny instant, they're essentially frozen in place, just like in a high-speed flash photograph. And that idea, that the atoms are frozen solid during the jump, is the absolute core of something called the Franck-Condon principle. Because the atoms don't move, the distance between them, the bond length, can't change during the transition. So if you draw this on an energy diagram, the jump has to be a straight vertical line up. It's a vertical transition. So, in the simplest case, the molecule's shape is basically the same whether it's in its ground state or its excited state. That means the most likely jump, the one that gives the strongest signal, is a direct vertical line between their lowest energy levels. But If the excited state prefers a slightly different shape, say a longer bond, then that vertical jump might land on a higher vibrational level, and that totally changes the way the spectrum looks. But what happens if that shot of energy is just too much? What if the electron gets kicked into a state that isn't just excited, but is completely and totally unstable?
Well, sometimes that excited state isn't a safe place to land. It's more like jumping onto a steep, slippery slope with no bottom. The very instant the electron gets there, there's nothing holding the atoms together anymore, and they just fly apart. We call this dissociation. And the spectrum you get from this isn't a set of sharp lines, it's just a broad, continuous blur, because any energy above the bare minimum will get the job done.
And then there's this even sneakier process called pre-dissociation. This is wild. The molecule jumps to what looks like a stable state. But if its energy curve happens to cross with an unstable one, the molecule can just hop over to the unstable state, and then poof, it flies apart. This is a dead giveaway in the spectrum. You'll see a series of nice, sharp lines that suddenly get blurry and fuzzy right before they might just disappear altogether.
And this is where it all clicks. This brings us right back to our big question. By reading all these clues, the positions of the lines, their shapes, their blurriness, we can actually work backward and decode the entire story of that molecule's breaking point. Okay, here is the absolute key to figuring this all out. A molecule's bond isn't like a rigid stick. It vibrates. And these vibrations happen at specific energy levels. As you pump more energy in, the gap between each of those vibrational levels gets smaller and smaller. It's exactly like climbing a ladder, where the rungs get closer and closer together the higher up you go.
The amazing part is we can measure these energy gaps directly from the fine details in the spectrum. And we see this beautiful, predictable pattern. The gap, which we call delta E, consistently shrinks as the vibrational level V gets higher. This pattern is the breadcrumb trail we've been searching for.
And this leads to this really elegant, almost beautifully simple technique called the Burge-Sponer method. If you plot these shrinking energy gaps against their vibrational level, you can literally draw a line and see exactly where that gap is going to drop to zero. That's the point where the ladder rungs finally merge into one. It's the exact point where the bond breaks. And the total area under that plot, that gives us the total energy it took to get there, the dissociation energy. And just like that, we found our answer. So let's just do a quick flyby of what we've learned. Shining light on a molecule causes a quantum leap from the HOMO to the LUMO. The incredible speed of that jump, explained by the Franck-Condon principle, is what gives the spectrum its unique shape. The details in that spectrum, blurry lines, broad curves, tell us exactly when and how a bond breaks. And finally, we can use those details to calculate the molecule's exact breaking point. Which kind of leaves you at this one last big thought. We've just learned how to read a story of molecular life and death, written entirely in light. And if we can learn all of that just by looking, it really makes you wonder, what other profound, incredible quantum stories are hiding all around us, just waiting for us to figure out the right way to look and listen?